Last time we began a problem applying Faraday's law to calculate an electric field from a changing magnetic field. And we said we had a current of I naught cosine omega t, so it's a time-varying current, which is going to cause a time-varying magnetic field, thus a time-varying magnetic flux, and then an EMF and an electric field. So what we did was we set it up for a solenoid, and first we're going to calculate the electric flux of the solenoid. That being the case, this is the electric field. The field and the line element are going in the same direction. They're parallel, and so the dot product, B dot dA, is going to be just B times dA. So this is my magnetic field. This is my dA, my area element. And when I integrate this, I'm going to get mu naught I N over L times 2 pi R dr. If I integrate that, I'm going to integrate that from 0 out to little r. I'm sorry, to big R, because I'm integrating the entire size of the solenoid, since I'm interested in the field outside the solenoid. When I do that, I'm just going to get 2 pi mu naught I N R squared over 2L. And of course, when I put my limit in, that becomes capital R squared. Well, that's the flux, but now I need to take the time derivative of that expression to get the induced EMF and thus the electric field. So to do that, I'm going to say, I know that the only time varying term is I. I know that di dt would just be I naught omega times the sine of omega t, negative sign out front. So my change in flux with respect to time then would just be minus 2 pi mu naught I naught omega times n times r times sine omega t divided by 2L, and of course I can cancel the 2's. That's going to be equal to the other side of the, on the other side, if I want to do 1.n dphi dt, I'm going to square the n as well. If I want to do negative n dphi dt to conform to Lenz's law, make that a positive. That's going to be equal to the integral of E dot ds, which is just E dot ds, which is just going to be equal to E times 2 pi r. Therefore, my electric field is just going to be equal to mu naught. Let's see, the 2's going to mu naught I naught omega n squared r sine omega t divided by 2 little r. And so that is my induced electric field that comes up as a result of a time-varying current. So this is a very nice example of how Faraday's law works. Now, what I'm going to leave for you to do is, at the end of the chapter, there are sections on motors and generators, and even a small section on how hybrid vehicles work. All of these work as a result of Faraday's law. A motor and a generator are basically devices that work in opposite directions. I'll let you read those and examine the PowerPoints. And I think we'll call that good for Faraday's law. And we will next time talk about inductance, I should say, before we move into a number of other topics. But I think this will be good for Faraday's law. It's an extremely important law. Now you have your fourth of the Maxwell equations. You have Gauss's law for magnetism, Gauss's law for electrostatics. You have at least half of Ampere's law, and now you have Faraday's law. We will, in a future lecture, complete Ampere's law so that you have all of Maxwell's equations and a complete unified theory of electromagnetism. Thank you.